All right, welcome to the team. So glad to have you. You're going to be working right on the core of our media system. So let's just start with the most important question. What actually happens when someone, anyone, hits that play button? It's a lot more complex and, honestly, a lot more interesting than you might think. Let's dive right in. This is the thing that should be on your mind every single day. Because what we do isn't magic. Even though it feels like it, it's a really, really carefully orchestrated set of solutions. Our whole job is to move these massive amounts of data across the internet, which, let's be honest, is inherently unreliable and congested, and somehow make it feel completely effortless to the user. And when I say massive, I mean it. To put this all in perspective, take a look at the raw data. A single 90-minute movie, totally uncompressed, is a staggering 791 gigabytes. Just think about that. Trying to stream that over any network? It's just impossible. And this right here is what we call the gigabyte problem. So our very first job, before a single packet even thinks about being sent, is to make that data manageable. This is where compression comes in. You have to think of it as the essential first step that makes everything else we do possible. We have to shrink that massive file down to a size we can actually work with. Now we've got two main tools for this job. First, there's lossless compression. This is all about perfect preservation. The file you decompress is mathematically identical to the original, super critical for things like text or medical data. But for media, we almost always use lossy compression. And the key insight here, it's not really about losing quality. It's a psycho-visual trade-off. We're sacrificing data that your eyes and ears can't perceive anyway for a file size we can actually deliver. So just for fun, let's look at how a classic lossless algorithm actually works. This is a Huffman tree. The idea is simple but totally brilliant. You assign shorter binary codes to the data chunks that show up most often. You build this tree by just repeatedly combining the two least frequent nodes until you're left with a single root. It's a foundational concept in data compression, and you'll see this kind of thinking everywhere. And it's really important to get a feel for the basic math here. To calculate the raw size of a video, you just start with the pixel count. Then you multiply that by the color depths to get the size of a single frame. Then you multiply that by the frame rate and how long the video is. This simple formula tells you exactly how big that mountain of data is that your compression codec has to shrink. Okay, so we've compressed the file. It's manageable. But now, how do we actually send it? You can't just use standard web protocols like HTTP for this. Real-time media needs a specialized protocol stack to make sure playback is perfect. So let's break that down. First things first, it is absolutely critical to understand that downloading is not the same as true streaming. With a progressive download, you're still basically saving the file to your device. Real-time streaming is a completely different beast. The data is played as it arrives and is pretty much never stored. This means you get near-instant playback, much better copyright protection, and this is a big one, the ability to broadcast live events. All of these are crucial for our services. So, how do we control the stream itself? Well, that's the job of RTSP. The best way to think about it is like a network remote control. It's not actually carrying the video or audio data itself. Its only purpose is to manage the session, sending commands from the client to the server, like play, pause, and tear down. The protocol that does carry the media? That's RTP. This is the real workhorse of the operation. It takes all that compressed audio and video, breaks it up into packets, and just ships them across the network. It's designed from the ground up to be lightweight and efficient for that continuous, real-time data flow. But RTP doesn't work alone. It's got a partner protocol, RTCP. This is the feedback channel. While RTP is busy sending all the media to the client, RTCP is sending reports back from the client to the server about the quality of the connection. We're talking things like packet loss, jitter, and delay. This data is absolutely vital for adapting the stream on the fly. And finally, in some networks where we have a bit more control, we can use something called RSVP. This protocol lets the client effectively say, hey network, I'm going to need 5 megabits per second for the next hour to play this video. And if the network agrees, it literally reserves that bandwidth, which goes a long way to guaranteeing a high quality of service. Okay, now we get to the final, and I'd say most challenging part of the whole system, that last mile to a mobile device. This is where a nice, predictable stream from our servers smacks right into a totally unpredictable environment, and that creates a whole new set of engineering problems we have to solve.
Yeah, unlike a desktop that's plugged into the wall with a stable connection, mobile devices are a minefield of constraints. We are constantly battling limited battery, weak processing power, spotty connectivity, and a crazy variety of screen sizes, all at the same time. Every single line of code we write has to be done with these challenges in mind.
So, how do we fight back against that awful intermittent connectivity? Well, our most powerful weapon is called adaptive bitrate streaming, or ABR. The client is constantly, and I mean constantly, monitoring the network conditions. If the connection starts to weaken, it seamlessly requests a lower quality video chunk. If things improve, it switches right back to a higher quality one. For the user, this all just means the video keeps playing. That dreaded buffering wheel, ABR is how we kill it. And to tackle that battery life problem, we just can't rely on the phone's main processor to do all the heavy lifting. Video decoding is incredibly intensive work. So instead, we offload that task to specialized, dedicated hardware chips that are built right into the phone's silicon. These hardware decoders are orders of magnitude more power efficient than trying to do the same job in software. Now, inside the device's operating system, there's another real-time battle going on. To make sure a video frame gets decoded and displayed on time, every single time, the OS uses these special scheduling algorithms. You might see something like rate monotonic, which gives higher priority to tasks that have to run more often, or maybe earliest deadline first, which dynamically prioritizes whatever task's deadline is coming up the soonest. So, we've covered compression, we've covered transport, and we've covered the mobile challenges. Let's zoom all the way out now and just look at the entire end-to-end system. This is how all those pieces we talked about fit together to create one single cohesive streaming experience. And here it is. This is the complete journey from start to finish. It begins at the source, where the media is captured and compressed. Then it lives on a media server, which is built to handle thousands of simultaneous streams. From there, it's transported over the network with our protocol stack. And finally, it arrives at the client, ready to be buffered, decoded, and played on the screen. So here's a crucial point. Once the data arrives at the client, its job is far from over. It has to manage synchronization. And there are two types. You've got inter-object sync, which is making sure the video frames within the video stream played the correct rate. Then you have inter-object sync, which is making sure the audio stream is perfectly aligned with the video stream. We all know how distracting bad lip sync is, right? That's a failure of inter-object sync. This whole synchronization problem is what makes our work so incredibly difficult. You're literally fighting physics. Every single packet arrives with a slightly different delay, and the server and the client don't share a common clock. And yet, despite all of that, we have to create a perfectly timed, seamless experience. It's one of the fundamental challenges of distributed computing. So I'll leave you with this question, something to think about as you start digging into our systems. When a user complains about buffering, where do you even start looking? Is it the encoder? Is it the server throughput? Maybe the network path? Or is the client's decoder just choking on the data? Understanding this entire chain, that is the absolute key to building and maintaining a world-class media service. Welcome to the team. I'm really glad you're here.